So my name is Sharon Fogel, and I am an applied scientist at AWS Research at Amazon. And I will present the work I did during my internship there, named ScrabbleGAN, which is aimed to generate handwritten images. So actually all the handwriting you will see in this presentation is generated using our model. And this was a joint work. Sorry. This was a joint work with Adar, Sarel, Shai, and Roy. So the main motivation for the project was handwriting recognition. So handwriting recognition is a very challenging problem, especially dataset-wise. So the problem is that unlike printed text, handwriting is much more hard to get and to label, because in printed, we can simply use the fonts we have in our computer to generate as many images as we want to. But handwriting has much more diverse style. Sorry. Okay, handwriting has much more diverse styles. So, and also you have the connectivity between the characters that you can't really simulate well in a computer. So, as it says here, every man has one thing he can do better than anyone else, and usually it's reading his own handwriting. And I know some people who can't even do that. So, it's a really challenging problem. So what we wanted to do is suggest a new way to generate images of handwriting and use these images to augment the data that we already have and get better recognition results. And we showed that we can also use it in a semi-supervised way for domain adaptation. Okay, so this is the general architecture of our approach, and it's based on a generative adversarial model. So first we have an input word, here it's meat, and we ask the generator to generate this word into an image of handwriting. And then this image is judged by two networks, the discriminator and the recognizer. So the discriminator is like a regular gun. It tries to distinguish between real and fake images. And there is a competition between the discriminator and the generator. And each of them tries to get the outcome better. The discriminator tries to distinguish better between the images. The generator tries to create images which look more real. And this actually improves the quality of the images and makes the generated images have more handwritten style. But this still doesn't mean that we'll have the content that we want inside the image. So we can have a gibberish image which contains another text from the input text that we asked it to generate, and it will still be okay discriminator-wise. And that's why we need the recognizer. So the recognizer tries to read the word inside the image. And this forces the generator to actually generate not gibberish, but the exact word that we asked it to generate. So we have two loss terms. One is for the style, to have handwritten looking style, and the second is for the content. Now let's go into the generator architecture. So we were actually inspired by the idea that handwriting is a local task, meaning that each character is dependent on the character before and after it. And the architecture is kind of similar to the game Scrabble. So like in Scrabble, where you have tokens representing the different characters, we have different filters representing each character, and we connect the different filters to create complete words and even sentences. So each character is inputted into the generator, which is fully convolutional, and then an output patch is generated in the output image. Now, all of these patches are actually generated simultaneously, and the convolutional layers create overlaps between them. And these overlaps are what allows us to create this cursiveness, the connectivity of the text, and also have some variance in the width of each character. So, for example, the letter M can take up all of the patch, but the letters E and T can take up only some of it. So these are a few examples comparing our approach to the previous state of the art. Now, the previous state of the art, they used a method which outputs the same output image size for all the words. So they were actually limited in the sizes of the words that they could generate. And also you can see the improvement in the quality of the text, especially for the shorter words. And you can see that in some letters, in the previous approach, some letters are missing, and they are not missing in our approach. Here you can see a few examples of the different styles that we can generate. So in each row, we input a different noise vector to the generator, and this results in a different style. And in each column, we use a different input word. So you can see the large variability in the connectivity, in the width of the stroke, and other factors. And you can also notice that the same character might appear differently according to the characters before and after it. So as I said, we can also use it in a semi-supervised manner. So here we used it for domain adaptation, and we used two datasets of English words, IM and CVL. So we assumed we have labels for the IM dataset, but we want to succeed testing on the CVL dataset. So as I said, in our approach, we have two networks, the discriminator and the recognizer. Now, the recognizer needs labels because it needs to identify the text inside the image. So for the recognizer, we use the labeled data, the IM. But the discriminator only needs to know whether the image is real or fake. So we can use unlabeled data. So we use the CVL data to train the discriminator, and this actually results in a style which looks like more like the CVL style. Okay. So to use this, we use the generator to generate new synthetic images, and then we augment the data that we have labeled, the IM, with the synthetic data that we generated to train a new recognizer architecture. And these are the results. So first we have the naive baseline using only the IM, only the dataset with the labels to train the recognizer. And we test it on CVL to see how many words we got wrong. This is the word error rate. And then we have sort of an upper bound. Assuming we did have labels on the CVL, what would be the improvement? And you can see that there is an improvement of about 17%, which is a lot. And this is the gap we want to overcome using our semi-supervised approach. So now we used the synthetic images to augment the IM dataset. So here we don't use any labeling on the CVL. We just use the images without the labels. And you can see that we have a 10% improvement in the results. So it's a large improvement. So just to sum up, we suggested a new way to generate new handwritten images. And we also showed that we can use it in a semi-supervised approach for domain adaptation. There are still some limitations to the method. So, for example, right now the width generated for each character is the same, so this limits the variability of the widths of characters we can generate. And also, right now, as I said, we simply randomly choose a noise vector, which results in a different style, and we would like to have more control over it and be able to generate the handwriting of a specific author. So we have ideas about how to do it in future works. So thank you for listening, and I leave you with a few quotes generated by our approach in a single forward pass. Thank you.